All right, welcome back everyone to the deep dive. Ready to get our hands dirty with some algorithms today?
Absolutely, diving right in.
Okay, good. So today we're taking a look at greedy algorithms. They're kind of like that friend who always goes for the biggest slice of cake.
Uh-huh, yeah, I can see that. Always grabbing for the most, right?
Right. But in the world of algorithms, greedy isn't always a bad thing. These algorithms are all about making the best choice at each step, hoping those local wins will lead to the ultimate victory, the best overall solution.
Yeah, think of it like taking shortcuts, but smart shortcuts. They're often simpler and faster than other methods like dynamic programming, but, and here's the catch, they don't always guarantee you'll end up with the absolute best result.
Exactly. There's a bit of risk involved, which makes it even more exciting, right? So today we're going to break down when these greedy strategies really work and when they might leave us hanging. We'll be dissecting some classic examples to see their strengths and also where they might fall short.
Sounds like a plan. By the end of this deep dive, you'll know when to confidently whip out a greedy algorithm and when to, maybe, consider a different approach.
Okay, so let's lay out the roadmap for today. We've got three main problems on the menu where greedy algorithms shine. First up, the activity selection problem. Imagine juggling a ton of meetings in a single conference room. How do you fit in the most without any overlaps?
A classic scheduling puzzle.
Then we'll decode Huffman codes. These are a clever way to squish down data, making those files nice and compact.
Data compression at its finest.
And finally, we'll tackle offline caching. Think of it like making sure your phone always has your favorite apps ready to go, no waiting for them to load. And to keep things balanced, we'll also touch on why greedy approaches sometimes miss the mark, particularly with the 0-1 knapsack problem.
Yeah, gotta see both sides of the coin to really understand the trade-offs.
All right, let's kick things off with maximizing our meeting schedule activity selection problem, front and center.
All right, picture this. You're in charge of a single resource, could be that conference room, and you have a whole stack of activities, each with its own start and finish time. Your mission: to squeeze in as many as possible without any scheduling clashes.
Right, no double booking allowed. And I guess if one meeting ends exactly when the next one begins, that's perfectly okay.
Exactly. They can be back to back, just no overlap. Now, you might think, well, to get the absolute maximum, I'd need to try every single combination of these activities. And to be fair, you're not wrong. We could go down the dynamic programming route, recognizing that a perfect schedule has optimal solutions for smaller scheduling problems within it.
Oh yeah, breaking it down into those sub-problems. But that sounds like a lot of work.
It can get quite intricate, for sure. And that's where the allure of the greedy approach shines through. It's all about finding a shortcut, a smart one hopefully, to the best solution. And the secret sauce here is figuring out the most effective choice at each step.
So in the activity selection problem, what's that golden move? What's the decision that sets us on the path to success?
Well, the winning move here is to always pick the activity that finishes the earliest. It's all about minimizing the downtime of that resource. Like get that meeting out of the way quickly so the room opens up for more possibilities.
Oh, I see. So it's like clearing the stage as soon as possible to make way for the next act.
Exactly. But how can we be certain that this strategy of picking the earliest finishers will actually lead to the most activities overall? It seems a bit too simple, doesn't it?
Yeah, is there a way to prove that this greedy choice actually leads to the optimal solution?
There is. We can demonstrate that the best possible schedule will either already have an activity with the earliest finish time, or we can tweak it to include one without messing up the total number of activities.
Oh, okay, so we're saying that even if an optimal solution doesn't start with the earliest finishing activity, we can always swap it in and still have an optimal solution.
Precisely. Let's imagine we have a perfect schedule, but it doesn't start with the activity that finishes the absolute earliest. There might be some other activity lurking around that finishes even earlier, right? Well, we can simply swap out that first activity in the optimal schedule with this new, earlier finishing one. And because this new one ends no later than the one it replaced, it won't cause any conflicts with the remaining activities in the original perfect schedule.
Oh, that's clever. So we've essentially proven that always starting with the earliest finisher never prevents us from reaching the best possible schedule.
Exactly. We're always on solid ground with this approach. Now, how do we take this idea and turn it into a step-by-step plan and algorithm?
Yeah, how do we actually make this work in practice?
Well, one way is to think about it recursively. Once we've picked our first activity based on its early finish time, we're left with a smaller but similar problem, right? We need to find the maximum number of compatible activities from the remaining bunch, all those that start after the first one ends. And then we just apply the same logic again, find the earliest finisher among those, and so on.
So it's like a chain reaction of picking the quickest meeting, then the next quickest that fits, and so on.
Right. And while recursion clearly shows how this idea works, there's a more efficient way, a more direct approach, called the greedy activity selector. First, we sort all the activities based on their finish times, nice and organized. Then we go through this sorted list, keeping track of the last activity we added.
I'm with you so far. Nice, neat, sorted list.
Good. Now, for each activity in the list, we check if its start time is after or equal to the finish time of the one we just added. If it is, great. It means they're compatible, so we add it to our schedule.
Okay, so we're just zipping through the list, picking any activity that starts after the previous one ends.
Yeah.
Makes sense. Now, in terms of speed, how fast are these algorithms? Does being greedy actually save us time?
Absolutely. If our activities are already nicely sorted by finish times, both the recursive and iterative versions take what we call theta n, where n is the number of activities. If we need to sort them first, that adds a little bit of time, ION LGN, to be precise.
Okay, so whether it's sorting or just going through the list, it seems like a pretty efficient way to solve this problem.
Exactly. It's fast, it's elegant, and it gets us the best solution.
So we've seen how being greedy can actually be a good thing when it comes to scheduling activities. But how do we know when a greedy approach is the right tool for the job? What are the signs that this strategy might be our best bet?
That's a great question. There are two key characteristics that often hint that a greedy approach might be the way to go. The first one is the greedy choice property making the best local choice leads to a globally optimal solution. We saw this in action with the activity selection, right? Picking the earliest finishing activity helped us maximize the overall number of activities we could fit in. What's really crucial here is that we made this choice without needing to worry about what was happening with the smaller subproblems.
Right. It's all about making the best decision in the moment without overthinking the bigger picture.
Exactly. And this is where it differs from dynamic programming, where we typically solve all those smaller subproblems first and then combine their solutions. Greedy algorithms, on the other hand, take a more direct path. Choose first, then solve.
So it's a more shoot first, ask questions later kind of approach.
In a way, yes. Now, the second crucial ingredient is optimal substructure. It basically means that the optimal solution to the bigger problem is made up of optimal solutions to its smaller parts.
So the smaller pieces have to be perfectly arranged for the whole thing to work perfectly.
Right. And in greedy algorithms, this usually becomes clear after we've made that initial greedy choice. We can then argue that taking the best solution to the remaining smaller problem and combining it with our initial greedy choice gets us to the best possible solution for the whole problem. So while both greedy and dynamic programming use this idea of optimal substructure, they apply it differently.
Okay, starting to see the nuances here. Now, to really get a grasp of when greed works and when it doesn't, let's dive into a classic problem where our intuition might lead us astray. The knapsack problem.
Ah, the knapsack problem. A perfect illustration of when greed can be both friend and foe. We actually have two flavors of this problem, the fractional knapsack and the 0-1 knapsack.
Two knapsacks, huh? All right, lay it on me.
So imagine you're a thief, right? You've got a knapsack and it can only hold so much weight. You stumble upon a treasure trove of items, each with its own value and weight. Now, in the fractional version, you're allowed to take pieces of items.
So like if there's a giant gold bar, I could just chisel off a chunk that fits.
Exactly. Now, does your greedy instinct kick in here? What would be the most greedy approach?
Well, I'd probably try to grab the stuff that's worth the most per pound, right? Maximize the value for every bit of weight I carry.
You got it. And in the fractional knapsack problem, that strategy works perfectly. You calculate the value per unit of weight for each item and then just load up on the item with the highest value to weight ratio until your knapsack is full. If you can't take the whole thing, you just grab a fraction.
Seems straightforward enough. Grab the most valuable stuff first, then move down the list.
Right, but then we have the 0-1 knapsack problem. A whole different beast.
Okay, what makes this one so different?
In the 0-1 version, you can't be so picky. You can't take fractions. It's all or nothing. Either you take the whole item or you leave it behind. And this little constraint throws a wrench into our greedy strategy.
Oh, I see. So if I go after that super valuable but super heavy item first, I might not have room for other smaller but still valuable items that could add up to more in total.
Precisely. You might end up with a knapsack full of just one or two big things, missing out on a better combination of smaller treasures.
So my initial greedy grab might backfire and lead to a less valuable haul overall. Sounds like those pesky overlapping subproblems are at play again.
Exactly. In the 0-1 knapsack problem, when you're deciding on an item, the leftover space and the remaining items create a subproblem you might encounter again through different choices. This overlap, combined with the fact that a simple, greedy decision can't guarantee the best outcome, makes the 0-1 knapsack problem a prime candidate for dynamic programming.
So for the 0-1 knapsack, we need to be more strategic, explore all the possibilities, not just go for the most appealing item first.
Right. It highlights the fact that while greed can be powerful, it's not a universal solution.
Great comparison. All right, let's shift gears now and explore another domain where greedy algorithms really shine. The world of data compression, specifically with Huffman codes.
Huffman codes are a brilliant example of how a simple, greedy idea can have a huge impact. The goal is to take a bunch of characters, each with a specific frequency of appearing in a file, and create a code that uses the fewest bits possible. Think of it like creating a super efficient shorthand.
So like if E is the most common letter in a text, we give it a really short code to save space.
You got it, but there's a catch. The code has to be prefix-free. This means that no code word, the unique binary sequence for each character, can be the beginning of another code word. This is crucial for decoding the compressed data later on.
Right, if one code was part of another, we wouldn't know where one character ended and the next began. It'd be like reading a sentence with no spaces between the words. So how do we build this optimal prefix-free code?
Huffman's algorithm tackles this beautifully. It constructs a binary tree from the bottom up, starting with the individual characters as leaves, each with its frequency of occurrence.
Okay, so we're starting with a forest of single-letter trees.
Yes. Then the algorithm repeatedly finds the two trees with the lowest frequencies and merges them into a new tree. The frequency of this new tree is simply the sum of the frequencies of its two children.
Okay, I'm visualizing this. We're essentially connecting the rarest characters first, creating bigger trees as we go.
Exactly. We keep merging until we're left with just one big tree, the root of our Huffman code. Now, to get the binary codes for each character, we trace the path from the root to the leaf representing that character. Each left branch we take is a 0-1, and each right branch is a 1-but.
So the more frequent characters, being merged later in the process, end up closer to the root and get shorter codes.
Exactly. That's the ingenious part. The most common characters get the shortest codes, leading to the most efficient overall representation of the data.
It seems so intuitive now that you explain it. Prioritize the least frequent ones for merging, and the common ones naturally get the VIP treatment with shorter codes.
It's a beautiful example of how a simple, greedy strategy can lead to an optimal solution. And just like with the activity selection problem, there's mathematical proof that this approach always works. These are often referred to as Lemma 15.2 and Lemma 15.3, which establish the greedy choice property and optimal substructure for Huffman codes.
So we're not just going with our gut feeling here. There's solid theory backing it up. What about the efficiency of Huffman's algorithm?
For ending characters, it typically runs in $1 NL time, which is very efficient. It uses a clever data structure called a min-priority queue to quickly find those lowest frequency trees at each step.
So Huffman codes are efficient to build and efficient to use. A win-win.
All right, let's wrap up our exploration of greedy strategies with a look at managing data in a cache, specifically with offline caching. Offline caching is all about minimizing those annoying cache misses when you have the luxury of knowing the entire sequence of future memory requests. Imagine you have a small, fast cache that can only hold a limited amount of data, and then you have a much larger but slower main memory. Every time your system needs data that's not in the cache, it has to fetch it from the main memory, and that takes time.
Right, it's like when your phone has to reload an app because it wasn't actively running. Frustrating.
Exactly. Now, in offline caching, we have this hypothetical scenario where we know exactly what data will be needed and when. It's like having a crystal ball for data requests.
So no more surprises, we know what's coming. How does this foresight help us?
Well, it allows us to use a greedy strategy called furthest in future. When our cache is full and we need to make space for new data, this strategy says to evict the block that won't be needed for the longest time.
Ah, so we're kicking out the data that's least likely to be used in the near future. Makes sense.
Right. And this strategy is often referred to as FIFO in its species of offline caching, even though it's quite different from the traditional FIFO used in online caching. By holding on to the data we'll need soon, we minimize those pesky cache misses. And just like our previous examples, the furthest in future strategy has been proven to be optimal thanks to those key properties: optimal substructure and the greedy choice property.
So perfect foresight equals perfect eviction decisions.
Hmm.
But how realistic is this offline scenario? Do we ever actually know the future of data requests?
Not usually. In most real-world situations, we're dealing with online caching, where we have to make decisions based on past requests. A very common online strategy is LRU, or least recently used. It evicts the data that hasn't been used for the longest time.
So it's going with the use it or lose it philosophy.
Exactly. And while LRU can be quite effective, we can analyze its performance by comparing it to the optimal performance we can achieve in the offline setting using the furthest and future strategy.
So the offline scenario gives us a theoretical benchmark, the best we could possibly do with perfect knowledge.
Precisely. It helps us understand the limits of what's achievable and evaluate how well our online strategies are performing.
That's a really helpful way to think about it. So we've journeyed through three key areas: activity selection, Huffman coding, and offline caching, where greedy algorithms consistently deliver optimal results. And in each case, we were able to pinpoint a specific greedy choice that guided us to the best possible outcome.
It's fascinating to see how those simple choices, applied repeatedly, can lead to such powerful results.
Absolutely. And just to recap, the magic seems to happen when two key properties are present: the greedy choice property, where our best immediate decision sets us on the right path, and optimal substructure, where the optimal solution to the big problem is made up of optimal solutions to the smaller parts. We saw this when we scheduled activities by always picking the earliest finisher, compressed data efficiently using Huffman codes by merging the least frequent characters first, and minimize cache misses in offline caching by evicting the data that's furthest in the future.
And let's not forget the 0-1 knapsack problem, where our intuitive greedy approach didn't quite cut it. It reminds us that not every problem that looks like it has a greedy solution will actually benefit from one. Sometimes we need a more comprehensive strategy.
Right, understanding the limitations of greedy algorithms is just as important as understanding their strengths. So for our listeners out there, here's a final thought.
Yeah.
Now that you've seen how and when greedy algorithms work, can you think of situations in your own life or work where taking the seemingly most obvious best next step might lead to the best overall result, or where a more short-sighted approach might lead you astray?
That's a great question to ponder. And with that, I think we've thoroughly covered the world of greedy algorithms as presented in this chapter. We've explored their successes, the core principles behind them, and those crucial situations where their limitations come into play. We touched upon the activity selection problem, Huffman codes, the furthest and future strategy for offline caching, and contrasted this with the 0-1 knapsack problem. We discussed the greedy choice property and optimal substructure, as well as the efficiency of these algorithms.
Thanks for joining us on this deep dive into greedy algorithms. Until next time, keep those minds sharp.